extreme deep field, looking out to the depths of space and time, which is sort of fitting with what Sandy will be talking about tonight. If you don't understand it, well, turn it over. We have about 300 words on the back to explain the Hubble Extreme Deep Field. As I said, if you didn't get one, you can get one on the way out. Our talk tonight is Sandy Faber from UC Santa Cruz, Cosmic Knowledge and the Long-Term Strategy of the Human Race. How many of you just came because that title was just intriguing, huh? All right, well, we'll have to see what she's really on about here. Next month, we have Nicole Lewis probing worlds beyond our solar system, okay? We've had a few talks in the last year about extrasolar planets. She's going to take it in another direction, okay? July and August, we have the dreaded TBDs, which means Frank needs to get his act together and recruit speakers. Summer is always hard to get speakers, but don't worry, have I ever let you down? In 14 years of running this, I have never let you down. We will have a speaker. All right. Those of you who drove in know that there is construction. This is more for the folks watching on the webcast. If you come here, San Martin Drive, south of Space Telescope is closed. You must approach from the north, okay? The website, if you want more information about our public lecture series, we have this link, hubblesite.org/go-talks, but it's easier just to say, throw into your favorite search engine, Hubble Public Lectures, and you'll find this. We revamped this a couple months ago where you have the links to the live event. We have links to the past lectures, and you can sign up for our email list right on our webpage now. Yay! All right, as well as links to upcoming lectures. Let's see, email if you want announcements. You can sign up on the page that I just showed you, or you can go to maillist.stsci.edu, public lecture announce, and provide your email address. We have not been spammed yet, so we've got a perfect spam record so far. If you have questions or suggestions or other ideas, you can send it to publiclecture@stsci.edu. If you do social media, Hubble has several types of social media. Facebook, not one, but two Twitter accounts, Google Plus and Pinterest. And if you like what I have to say and want to hear more of it, I have a blog, Hubble's Universe Unfiltered on Hubble site. That actually will I have a new episode coming out on this Friday, so that'll look for that. I'm also a little bit on Facebook, Google Plus, and Twitter, but I don't spend too much time doing those things. There's just too many other cool things to do. All right. The observatory will not be open tonight. If you looked at the sky on your way in, sorry, we're not going to have any observing session tonight. Okay, but every Friday night, the Maryland Space Grant Observatory does run observing sessions, so go to md.spacogrant.org and find out when they are going to be open, okay? Now, news from the universe for May 2016. My first story tonight, the lunatic fringe. Now, those of you who understand lunatic know the root word luna means moon, okay? And fringe is out at the edge. So what this story is really about is moons at the edge of the solar system. So what's out at the edge of the solar system? This is a plot from the Minor Planet Center of the outer solar system, and these green lines here are Neptune, Uranus, Saturn, and Jupiter, the orbits of the giant planets. And all of these red and white dots out here are the Kuiper Belt objects, or the trans-Neptunian objects, depending upon which camp, how you like to pronounce it. And every single one of those has been discovered since 1990. Well, every one about one, which was discovered in 1930, okay? So we have a whole suite of objects out here, the Kuiper Belt objects out there, a new region of the solar system, okay? And what are they like? Well, here are some of the largest ones. Here is our moon for comparison. This is Triton, the largest moon of Neptune, which is almost assuredly a captured Kuiper Belt object. And then we have Eris, Pluto, Makemake, Haumea, Sedna, and Quaoar. Okay, yes, that's its real name, Quaoar. All right, and you can see that we've got a lot of these relatively large objects out in the Kuiper Belt. And Hubble has been helpful in exploring them because while they look, they're all smaller than our moon. They're relatively large for the Kuiper Belt. They're really, really far away, so they're really, really small in the sky. So you need Hubble's high resolution to be able to help study them. So we know that Hubble has been extremely helpful in studying the Pluto system. We knew about Pluto and Charon when Hubble was launched, but Hubble discovered Nix and Hydra in 2005, 2006, and then Kerberos in 2010 and Styx in 2012. Hubble discovered 4 moons in the Pluto system, okay, because of its high resolution. And then some people say, well, look, Pluto has all these moons. It should be a planet, right? No. If we look at the 4 largest Kuiper Belt objects, Eris, Pluto, Makemake, and Haumea, all of them have moons except for Makemake, okay? Actually, now this diagram was made a while ago before we visited Pluto, and it lists Eris as being bigger than Pluto. We now know that since we've flown past Pluto, that Pluto's probably slightly bigger than Eris. So we should reverse those two, but I'm not going to update my diagrams every single time. I've got way too many of them to do. All right, so Makemake is the only one that doesn't have a moon, right? Wrong, because Hubble did studies of Makemake and has been looking and has not found anything until we got this image. Okay? This is Makemake in here. You can see it's actually got diffraction spikes that make it look like a star because it's really overexposed. And then we see that small dot there. That small dot there is labeled S2015-136472, which nobody ever remembers, so we have actually just called it MK2. That is a moon of Makemake. All right, and Makemake is about 1,400 kilometers across, whereas MK2 is about 1/10 of it, around 160 kilometers across. And it orbits about 15 Makemake radii away. So our moon, for example, orbits at, Makemake diameters. Our moon orbits at 30 Earth diameters, so this is orbiting at 15 Makemake diameters. So that's, relatively similar. And the reason why it's so overexposed is that Makemake is 13,000 times brighter than MK2. So we really had to totally overexpose Makemake in order to be able to see MK2. All right? So we now can put up a cool diagram of the outer solar system. All right, here's Earth and Moon to scale. We've got Pluto, Eris, Sedna, Makemake, Quaoar, Orcus, Haumea, and 2007 OR10, which, by the way, holds the trivial title of being the largest object in the solar system without a name. All right, and you can see that we have moons for almost all of them except for these two, Sedna and 2007 OR10. Quaoar has a moon and Orcus has a moon. So right down here, you can see these are the objects we would call the lunatic fringe, and we are still filling out our census of the lunatic fringe in the solar system. All right, second story tonight, a cosmic birthday balloon. What? Do you have a question?
Are there any moons that have moons?
Are there any moons that have moons?
They have moons?
I know of asteroids that have moons. I do not know of moons that have moons themselves, okay? That you get into the gravity of it when if it's got to be well separated in order for a moon to be stable around something, right? So if you have a moon that's relatively close to its Kuiper Belt object or planet or asteroid, and you try and put another moon around it, the gravitational perturbations will actually disrupt that system if it's too close. They need to be widely separated for the separate orbits to be stable. Okay? So I know of none. All right?
Whoa.
Yes. Other question?
One of the objects that you showed, the one that starts with an H.
Haumea?
Yes, it's the only one I've ever seen that's oval. Is
Yes.
that accurate or is that a mistake?
That is accurate. Haumea is not spherical. All right?
How did
Haumea presumably underwent a very large collision. There is Hayaka and Namaka, which are two large moons of Haumea, but we've also discovered a series of Kuiper Belt objects that appear to be on a similar orbit as Haumea. leading us to understand that Haumea underwent a very large collision, producing this shape as well as its rotation. Okay, so it was put into a lot of spin, which can also produce that shape. And then there's other debris along its orbit, okay, that would fit in with the collision hypothesis. Okay, good catch. All right, back to our birthday balloon, because last month is, of course, the 26th anniversary of Hubble being launched into space and placed into orbit. 26 years of this telescope. And every year we put out a pretty picture to celebrate the birthday. And I can actually tell you, Zolt LeVay is sitting here in the audience. It's a lot of pressure on the people who have to choose the image. Zolt is one of them, to try and go, what can we do to top ourselves this year? Okay. So this year we're going into the constellation of Cassiopeia. Can we take the down lights down just a little bit more, Thomas? Can we take the lights down just a little bit more, because this is a dark slide. There we go. You start to see. All right, everyone see the W here? All right, that's the W of the constellation Cassiopeia. We're going into the constellation of Cassiopeia, and you can see that a river doesn't run through it. It is the Milky Way that actually runs through Cassiopeia. All right? So if we zoom in a bit, we can see inside that Milky Way there are some nebulae along the Milky Way through Cassiopeia. We come in a little closer, we can see a nice star cluster down here, but the nebulae we're looking at here, and this, when we zoom in, is the Bubble Nebula. About 30 arc minutes across from top to bottom in this image, about the size of the apparent size of the full moon on the sky. All right, and the Bubble Nebula is really kind of cool. All right, this is just from Worldwide Telescope, the Sky Survey, but if I take the National NOAO image, you can see a really nice image of the Bubble Nebula. This is not the Hubble image, okay? This is kind of cool, but it's not the Hubble image. We got something even better for you. What's really interesting about this nebula is that this one star here in the center, okay? That star right there is was born a 60 solar mass star and is responsible for ionizing all the gas of this nebula, okay? Usually we think of these nebulae, we got a bunch of stars in the center. This is one star that's truly responsible for the entire nebula. It's also responsible for this bubble, but I'll talk about that when I show you the Hubble image. The Hubble was not able to get the entire nebula. We were able to get, with a mosaic of 2x2 pointings, this view of it. And so for the 26th anniversary, we released that image there. Ooh, cool. No, it's not cool, okay? Because this image is actually 59 million pixels. You can't see squat yet. So let me zoom in and show you full resolution details, okay? So let's go, it's beautiful, but let's go in and see some of the real details, okay? This is full resolution. Now you're starting to see that star in the center, and look at all the delicate tendrils of gas around it in the bubble. All right, if we go to the edge of the bubble, you can see how the material is being blown out, okay? Assembles into these wafts along the edge of the bubble. We can also see the pillars in the upper left, that the ionization from that star is eating away those pillars like we see in many of the other nebulae. And what's really cool is right behind the bubble, there are some pillars that are actually pointing towards us. Okay, so normally we see the pillars and you see them sideways. These pillars are actually pointed towards you. We're seeing the tops of the pillars, all right? So we get together to see this bubble, all right? And what we've got here is the ionization from this star has created this big nebula way out here, but this star is actually so massive, it's blowing away its outer layers. It has a mass loss wind. Now, it's not losing much per year. It's only 10 to the minus 5 of a solar mass every year. But if you add that up for 4.5 million years, you get a significant amount of mass loss. It is the greatest diet plan in the universe because this star has gone from 60 solar masses down to 45 solar masses. It has lost a quarter of its weight in this wind. Where's all that material? Well, that's what forms the the bubble here, okay? The material streaming off goes out. The other thing you may notice is that this star is not at the center of the bubble, okay? You can see that there is pressure. Basically, you got to understand this by pressure. There's pressure pushing out this bubble. The wind creates pressure to push out this bubble. But the ionization fronts along here actually have a pressure pushing back, so it can't expand as fast in the direction toward the ionization front as opposed to the regions away from the ionization front, okay? Also, towards this pillar here, you can see that there's a lot of structure in here caused by the bubble expanding toward that pillar that's sticking up. So the bubble is expanding here and it's actually flowing around those pillars there. So you got a really complex structure going on, a mass loss wind from this star going out inside this large cavity of the nebula. All right, and since we've got all that three-dimensional ideas and structure, what are we going to do with it? Well, our team gets together, we take this Hubble image, we put it on top of the NOAO image, we sculpt it in 3 dimensions, and we give you a fly-through to the Bubble Nebula.
Oh, man.
And you're scoring.
Yes, it does cry out for some good music.
Oh, gosh.
That's your star. 2008.
Yes, this is the star in the center here.
Yes, here.
What's the diameter of the bubble?
About 7 light years across. So, and that's the bubble we put together to say,
How long did it take to lose that?
About 4.5 million years old. The star is about 4.5 million years old, and it'll probably live for 10 or 20 million years before it explodes as a supernova.
How far away is it?
7,000 light years? Yeah, about 7,000 light years.
It's lost about 15 solar masses. Is most of that concentrated at the edge of the bubble, or is it evenly distributed?
It's mostly concentrated to the edge of the bubble because what it sort of forms a snowplow. In astronomy we call it snowplow physics because the material that's going off here is moving quickly and then it just sort of slows down and gets pushes against stuff that's pushing back against it. So it is mostly toward the edge. Also, you get limb brightening because a thin bubble, if you look face on through it, you don't see much, but when you look edge on through it, you get higher density. So you get limb brightening on the bubble as well. Yes?
Does the star have a name?
The star does not have a good name. It's BD blah, 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 blah. Okay, we call that a phone number. All right, so the star only has a phone number, not a name. All right. Yes?
You said something at the beginning of the talk when I walked in. I was late. Excuse me, first off about that. But it was the largest mass in the something, but it had no name.
Oh,
yeah,
2007 OR10. Right, it's the largest object in the solar system that does not have a name. And it's not my responsibility to give it a name, okay?
I know, but I think that's interesting.
Yes. All right, so we'll call it Sam. We have a suggestion from the audience. We'll just call it Sam, okay? So I'll read you that plot and I'll call it Sam. Talk to the AAU, okay? It's not my bailiwick. All right, let me get on to our featured speaker because we have an amazing speaker for you tonight, okay? She's our Carolyn Herschel visitor, and so she's wonderfully agreed to give us a talk here. Her BA is in physics from Swarthmore. She got her PhD in Harvard, and she is now university professor at UC Santa Cruz, as well as a staff member at the UCO Lick Observatory. She has an amazing career in cosmology and galaxy formation, and she's done like over 300 papers, if I remember correctly. So let me just give you a couple of the highlights. She helped establish cold dark matter as the basis for galaxy formation, which, by the way, enabled my PhD thesis. Thank you. CDM was a big part of the simulations I did for my thesis. She is the Faber in the Faber-Jackson relationship, which is a scaling law for galaxies. She helped diagnose the optical flaw in the Hubble Space Telescope. She played a big role at the Keck Observatory in Mauna Kea, both in the rationale for creating the observatory and has been a major user on both the DEIMOS and the DEEP project. She has numerous awards and prizes, which I could read off to you, but you'll have to take my word for it. She's amazing. She's a member of the National Academy of Sciences. And finally, in 2013, President Obama awarded her the National Medal of Science. If you're... If you're not impressed now, just wait till you hear her speak. Ladies and gentlemen, Dr. Sandy Faber.
Thank you, Frank. I think we should all start out by congratulating Frank's department and the other folks at the Institute who produced these beautiful pictures. I mean, this is art for the ages, don't you think? And these fly-throughs have taken the whole enterprise to a new level. So,
to a new dimension.
Absolutely, absolutely. So I've heard nothing but good things about you. I've been told that you are really sharp and that I should not talk down. I can put in some big words. And that you'll probably ask a lot of good questions. So this sounds very encouraging. I'm very glad to be here, and I hope we'll work together on this talk. Actually, this is a new talk, and I'm still working on it. As you can see, it's a little experimental, it's a little weird, it's a little different. I'm not just here to talk about the universe, I'm here to talk about the implications of the universe. Now, my title is a little dry, Cosmic Knowledge and the Long-Term Strategy of the Human Race. Here is the title I wish I could have used. Okay. This is a book, unfortunately somebody thought of this first. Timothy Ferris wrote this book called Coming of Age in the Milky Way, and this absolutely captures what I'm trying to convey tonight. In a nutshell, for years I've been challenged, myself and by others, why do we care about this astronomical knowledge? What good is it? Remember that old expression, a chicken in every pot and a car in every garage? I don't think we could say that astronomers have ever done that. In fact, we had a big discussion at dinner as to how we could convince the NSF that astronomy is really important. Well, I've developed a chain of argument for this, and I hope to try it out on you tonight, and I'm hoping that I'll get some feedback from you as to whether you think it's a bunch of garbage or whether you think it's promising. And the essence of it here is in this title, what happens when you come of age? When you come of age, what does that signify? It means that you are through your infant period. You have learned what you need to function as a mature member of your community. You have knowledge, that's very important. You don't come of age without knowledge. And you have to take responsibility. And I think that's characterizes our generation of humans with regard to cosmic knowledge. And so the essence of my talk, I'll get to it at the end, is what are we going to do with this cosmic knowledge? Nothing? Or is it in fact very precious, and should it be informing our every next move? So I'm not going to actually answer that question, please don't get your hopes up, but I will pose it, and I'd be very interested if we could have a discussion. Okay, so my talk here is in 3 parts. The first part is cosmic origins. I have to set some stage. Then the second part is building a planet. That's planet Earth. The third part is glimpse of the future. And that's really what I mean by cosmic knowledge. If you understand the past, then you ought to be able to predict the future. We are now in a position to predict the future for the human species, cosmically speaking. There are some profound consequences here, in my opinion, and what are we going to do with that knowledge? Okay, so again, setting the stage cosmically speaking, this is the early universe. Almost smooth, but with small density fluctuations, about 1 part in 100,000. Note the time, 10 to the minus 35 seconds after the Big Bang. Temperature, 10 to the 27 degrees Kelvin. Not conditions that we see around here today. Now, the important thing about this is that the density was not uniform. It's these fluctuations at about a part in 100,000. They formed, they were the seeds of structure that we see in our universe today. This is a wonderful simulation by, let's see here, can I get down there? By some Japanese. Okay, let's watch it. This is galaxies forming. What they did was they put, I'm having trouble. Here we go. Let me start up here again. There we go. Okay. What they did was they put in density fluctuations. And the density fluctuations, where there are peaks, they draw in matter as the universe expands. And so this is a simulation of how galaxies actually form. And the peaks are mostly in this so-called dark matter, which we don't see in this simulation. This shows us gas, which is condensing to make galaxies, and within the galaxies, stars are forming. So the little white dots that you can see here, maybe you should look up on these screens, get a better view. Those are the stars forming within the galaxies. So we start with sort of a filamentary structure. The filaments drain to nodes. That's where the big galaxies form. And the whole process is very chaotic as these proto-galaxies merge with other proto-galaxies to make larger structures. And every time they merge, whatever pre-existing stars had formed get disrupted and get thrown into a quasi-spherical halo. And remaining gas, which is constantly falling in from larger distances, reforms and tends to make a disk. And then another collision happens, and the stars get thrown into a halo, and then the disk reforms. So this is our basic picture for how galaxies formed, like our Milky Way. Okay? So why do we believe this? Does this match the structure of galaxies that we actually see? It actually does. Let's look at some pictures of galaxies. All right. Here we see the familiar spheroid, this round structure surrounded by a disk. Here's the disk, right? The galaxies that we see are different mixtures of these round spheroidal structures surrounded by disks. And the ratio depends on the disruption pattern during when the galaxies actually formed. And now we can look at some galaxies edge on, and we can actually see the flattened structure very visibly and this roundish structure in the middle. All the fossil disrupted galaxies, the older stars in the structure that were thrown into a spheroid by those collisions. And here is our own galaxy, taken with a wide-angle lens. And we can see, there's a little bit of distortion in the camera, but we can see very clearly that we have that structure. We have a flattened disk of rotating stars. We have these dust clouds, and we have a spherical structure of scattered stars that were thrown into those circular orbits a long time ago. Before we move off this picture, I want to call your attention to these dust clouds. They're going to be a continuing theme in my talk. They are made in the atmospheres of stars, thrown out into the interstellar medium, and then they grow there by accreting more heavy elements like iron and silicon and carbon from the interstellar gas. We call it interstellar dust, and it creates a very characteristic absorption pattern on top of the light of galaxies. Okay, now, in addition to checking our theory by looking at the structure of nearby galaxies, we can make even better tests thanks to Hubble, because Hubble takes very deep pictures like this one, the Hubble Deep Field, and we've measured the distances of objects. Each one of these objects has a distance that can be measured either from ground-based telescopes or even from Hubble itself, rough distances. And Frank has made a wonderful movie which allows us to fly into this picture. And as we fly into the picture, we're flying out in space and back in time, because it takes time for the light to get to us. And finally, well, the first thing we notice is that as we fly down that arrow of time, the galaxies change, they get smaller. And this is what the theory predicts, because galaxies grow from this gravitational accretion process. The early ones should be small, that's what we see. The early ones should be disturbed, because that's when the collisions were more violent. That's also what we see. And finally, we get to a point where we really run out of galaxies. We can't see any anymore. They probably exist, but they're too small to be seen even by Hubble, and that's why we need JWST, because it will see those small objects. Now, when you look at a picture like this, you could get rather depressed. You know, I love this company. You know this company? It's called Despair, right? Actually, this is my own invention, modeled on the theme of the Despair poster. I just love those posters. Okay. And why would you get why would you feel some measure of despair looking at this picture? Because there's so much stuff there, and our galaxy could be any one of those, you know. There's just doesn't seem to be anything special about us. There's just a lot of stuff in the universe, and we're small and insignificant. But actually, I don't feel that way at all. And I hope you will come away with my talk, one of the messages from my talk, that you will understand that actually we seem to be very special on this planet. If we're not unique, then we're at least very good. Okay. And special things happen here that can't happen elsewhere. So don't feel depressed, stay tuned. Now, we made galaxies, and galaxies are important because they are the environments for making stars and planets. Stars form from dense clouds of gas within galaxies. Here's an example. Okay. Again, another lovely Hubble picture, blowing it up and showing us all the structure. This is a generation of young stars that's blowing a hole in the birth cloud gas. We see lots of these regions with Hubble. I'll show you a couple of pictures here. This one is my favorite, this next one. Okay, so I love this. I mean, this is the cluster, the big cluster, and it's blowing a photon rain, and the photon rain is sculpting these pillars, which we see everywhere in these star-forming regions. But what I love about this picture is this little guy in here, right? We talk about man caves. This is a star cave. Okay, so this guy formed in here and is, or gal, and is blowing a little hole, and fortuitously we can look right into that and see it with a beautiful Hubble picture. Okay, now, actually, the region where we learn the most about the star-forming process is a little bit closer to home. It is the famous Orion Nebula. So let's blow up the nebula, that sword in the belt. These are, again, Hubble pictures. And taking advantage of the Hubble resolution, we're going to zoom in, zoom and zoom and zoom and zoom, and see what kind of structure that we see. So let's do that. And every time we blow up here, I show you the scale. And finally, this last region, you can see all kinds of weird things here. And in fact, almost 60 of these things have been counted in the Hubble Nebula. And they fall into two categories. This is the first category. These are the young ones. These are young solar systems, young stars just in the process of forming. And the more mature ones look like this. So here is a formed star, and there was material that collected around it in a rotating disk. Remember the dust that we saw in the first picture of the galaxy? The dust in the interstellar medium has collected to make a disk of rotating dust around these protostars. These are protostellar nebula. How do we know that they're flattened rotating disks? Well, fortuitously, there's one edge-on guy in Orion that shows it to us very clearly. You can see they're quite big. 17 times the size of Pluto's orbit takes us well out into the Kuiper belt of objects in our solar system. Now, why is this dust important? It is crucial because it's the first stage of planet formation. These little dust grains, which are about 1 micron in size, that's about the size of a wavelength of light, they are sticky. They stick together even in the nebula, and they coagulate to make larger structures. And then gravity takes over and builds even larger structures. The point is that this dust is the beginning, as far as we know, of all planet formation. Doesn't matter whether it's a Jupiter or an Earth, doesn't matter what the size of the planet is, this is how planets start. And here's a picture of a rotating protosolar nebula with these rocky objects in it, right? Okay. And we're flying into it, so we're flying past some of these objects. The ones that don't coagulate into planets are asteroids. This is not even, this is an artist's imagination. I wish it were a simulation. Okay, so I'm going to show you what to me is one of the most iconic images that anybody has ever taken about life on Earth and the formation of planets. And here it is. An absolutely jaw-dropping picture, a real picture, taken in Arizona by this very talented photographer, Wally Pakolka. And why do I like it? Because here's rocks, and here's the stuff that the rocks came from. So when you hold a rock in your hand, what you're doing is holding particles of interstellar dust that at one point were floating out in interstellar space. So this shows to me the essential unity of our home here, Earth, with the rest of the universe. We are truly children of our universe. We belong here. The universe made us. And this is the kind of knowledge that religious cosmologies are seeking. And yet modern science has just put it here for us on our plate to understand. Okay. Now, we've seen up to now that there seem to be galaxies everywhere. Interstellar dust is ubiquitous. Presumably when we look at another galaxy and we see that it's full of this dust, it is also making planets, just the way our galaxy is making planets. So making galaxies and dust and planets seems to be an easy process. In the next part of my talk, what I want to address is the characteristics of our solar system, and Earth in particular, as compared to what we're learning about other planets in our galaxy. So there are two views. The first view is that we're nothing special. It's called the Copernican principle. Sometimes it's called the principle of mediocrity. Sometimes, and the conclusion is that Earth-like objects would be common. This has been a very useful principle in cosmology. It has worked up to now. There's nothing special about our location in the universe. There's nothing special about our sun. It's an average G-type star. Nothing special about our galaxy. This is the so-called Copernican principle. And something follows from that, something called the Drake equation. Very famous man, Frank Drake, who was one of the first people who tried to start thinking about how rare intelligent civilizations would be. And he, using this principle, wrote down this equation. The number of intelligent civilizations in the galaxy is proportional to the number of stars in the galaxy, n star, times a bunch of factors, the fraction of suitable stars, et cetera, right? I'm not going to go through this equation, but I note that there are 6 terms in it. And if there are 100 billion stars in the galaxy, and each one of these terms is 0.1, which it turned out to be, as he figured out these numbers, a tenth, then the net result was that there were 10 to the 5th, roughly, intelligent civilizations estimated from the Drake equation. Fine, okay? Now, there's another way of thinking about this. There's another book, a book called Rare Earth by Ward and Brownlee, and they take a different view. Why complex life is uncommon in the universe, and their principle is the principle of singularity, and it leads to the conclusion that Earths are exceptional. And why does it do that? Because they have a different equation. Okay, they start with a number of stars here, but they have a lot more terms. They have 5 more terms in their equation than the other one. Is it 5 or 4? Something like that. Okay, so the question that these people are grappling with is, how special does an Earth have to be in order to make an intelligent civilization? How many factors do I want here? And just to mention one that we'll talk about in a moment, magnetic field. Frank Drake didn't put a magnetic field in his equation. He doesn't have a magnetic field factor, but these people do, F sub m, okay? So the challenge for us is to try to figure out how many factors we need, how many factors are really interesting for life and how many factors for complex life. Okay, so if there are 4 more terms here, if the original equation gave 10 to the 5th simulations, and I add 4 terms, and every term is 0.1, then this equation is going to be 10 civilizations, right? What I'm trying to say is that people like to say that this number, the number of stars, 100 billion, is so big that it has to be inevitable that you're going to wind up with a lot of intelligent civilizations. My point is that that's not true, that depending on how many factors we think are crucial, we can just keep adding them, you know, and it's going to make the probability smaller and smaller. Okay, so let's consider some of these properties now. The first thing that we have to do is we have to start with the host star properties. And the host star can't be too hot because hot stars have ionizing radiation and they also have short lives. And it's taken us 5 billion years to get to this point on Earth, so we need long-lived stars. On the other hand, it might not occur to you, it was new to me, the stars can't be too cool because little stars, called M stars, have dangerous flares that might send out charged particles. And they have another problem. Their habitable zone is too small. Let's look at that. Here's a picture of habitable zones. This is clearly the key feature in deciding whether a planet is going to host life or not. If it's too hot, what you need is a planet that has the right temperature to have liquid water on its surface. Okay? So if it's too close, it's going to be too hot and the water is going to vaporize. If it's too far out, the water is going to freeze, and so you want this so-called Goldilocks zone here that is just right in the middle. Okay, so now let's consider what habitable zones do as we change the brightness of the stars. So an A star is a pretty hot, bright star. Our sun is a G star. And then this little star that I was just talking about, the M star, is dim. Well, if the star is dim and we need to be warm, then we need to get close to the star. And so the habitable zones of M stars are tiny compared, this picture doesn't actually do it justice. The habitable zones are very close in, and then something disastrous happens to the planet. When you get too close to your star, then you become tidally locked. And the moon is tidally locked with the Earth. That's why what we mean by having the same face of the moon, the same side of the moon pointing to us all the time, this planet would be tidally locked with its star. That means that one side would always point to the star. That means it would be perpetual day on that side and perpetual night on the other side. So this is going to set up a ridiculous climate that's very different from the climate that we have on Earth. And many people think that that is not the kind of situation for intelligent life or complex life. Okay, a couple more things. Metal-rich planets. Why metal-rich? They have to be metal-rich because they have to have these dust grains. Stars and nebulae that are very low in heavy elements, don't have iron, don't have magnesium, don't have carbon, just have hydrogen and helium, they are not going to have dust grains. And so they're at a great disadvantage in making these planets. And finally, you can't be too close to the galactic center because we think that big galaxies like ours generate very active black holes at some point in their lifetime, and the fierce radiation coming out of that black hole could scour the planets and sterilize them of life. So you better be in the outer parts. And you will have noticed that all of these properties are exactly the properties of our solar system. Okay, let's move on. Let's look at planet properties themselves. As far as planets go, you can't be too big because big planets have the wrong composition. They have envelopes of gas, hydrogen, helium, methane, and so on. And they have very heavy atmospheres. Examples are Jupiter and even Uranus and Neptune in our solar system, too big. But you had better not be too small for a couple of reasons. First of all, if you are small, then your gravity is weak and your atmosphere can escape to space. And this can even be accelerated by the fact that your core, your iron core, can freeze out. And it's a molten core with convection in the core that generates what we call a dynamo. That's what makes the magnetic field. And the magnetic field of Mars, which it doesn't have, would divert the solar wind coming out of the sun. The solar wind is a blast of energetic particles that scours away atmospheres. If you don't have a magnetic field, you are open to the solar wind, and you can lose your atmosphere. So that's what this second point says. So on 2 points, Mars was disadvantaged by being too small. Okay, so here's another point about being the right size. There's something called plate tectonics on Earth. Sometimes we call it continental drift. In the last 40, 50 years, we have discovered that continents move around. And this drifting process, the continents are riding on crust. There's convection in the mantle, and these convection currents come up and they entrain a continent, move it this way, and on this side the continent moves that way. So we have paleological evidence that the continents have constantly been moving for billions and billions of years. We know this is happening. Okay, now why is this important? I made an important comment here, an essential feature. People who consider the habitability of planets just after being in the habitable zone, which has got to be the most important thing, just after that, it is thought that a planet needs plate tectonics. And why is that? The first thing is that this carries heat. You know, when you heat water on the stove and it convects, it's convecting because it's carrying heat out. And in the same way, we have a hot core and the convection cell is carrying heat away. It allows the convection in the mantle and also the core, and that is what's powering our magnetic dynamo. I just mentioned that before. So a cool surface is what you need to get a magnetic field. And a cool surface is permitted by plate tectonics. Okay. Now, here is a really new thought. Actually, plate tectonics is our thermostat on Earth. There are reactions that occur as new rock comes up and gases into volcanoes, putting carbon dioxide into the atmosphere. Carbon dioxide, greenhouse gas, remember that, right? Okay, but as a result of chemical reactions in the rocks, at the same time, carbon dioxide is removed from the atmosphere and it's sequestered in deposits that go onto the seafloor, which are then subducted. This crust is being brought down back into the interior of the Earth. And so we're producing CO2, but at the same time, we're resequestering the CO2. CO2 being our major greenhouse gas. This opposing effect opposes a runaway greenhouse, and this is actually the most important element in the stability of Earth's climate over billions and billions of years. And we have evidence, as we'll see in a minute, that planets that don't have plate tectonics have unstable climates. And finally, the last point is, this really was something new for me. Did you know that early in the Earth's history there wasn't any land? That we were a water world. There's enough water to cover the whole land because there weren't any continents. Plate tectonics actually builds continents. They build up here on the Earth's surface as a result of material brought up. And so the last reason to have plate tectonics is to build continents and create land. And we think that land is important for diverse life on Earth. All right, so let's say a little word about water. Very hard to get and hard to keep. We know that it's needed as the solvent for life, but what you might not know is that water is crucial for softening the crust. If you don't have water in the crustal rocks, they're too stiff to go back down again with plate tectonics. And so having enough water on your surface is another ingredient in plate tectonics. The Earth has a lot of water. We don't know exactly where it comes from, but there's probably generally more water farther from the sun in the protosolar nebula, which means that Mercury and Venus didn't get as much. Speaking of that, Venus lost its water. It was too close to the sun. Its water evaporated, it vaporized. Mars also lost its water. It was cooler, but it was too small, couldn't hang on to its atmosphere, plus it had no magnetic field, and so its atmosphere got scoured by the solar wind. amazingly, Earth has just the right amount of water to fill the ocean basins. Did you ever think about that? Who ordered that? You know, this is a key factor in terrestrial climate. Should we put a factor in the rare Earth equation for having the right amount of water that will just exactly match the size of the ocean basins of that planet? Well, nobody knows, but there are people who do think that having just that amount of water leaving dry land, and not too much of it, is exactly what's needed to facilitate life. I mentioned Venus a couple of times. It's a study in tipping points. It's almost the same mass and radius of the Earth, sometimes called our sister planet, but is slightly nearer the sun. That slightly made a huge difference. Today, the atmospheric pressure is 90 times that on Earth, and the temperature would melt lead 870 degrees Fahrenheit. No oceans, no continents. Why? Completely different from Earth. Well, it was closer to the sun, stayed hotter longer, got less water by being there, and whatever water it had vaporized out of rocks into the atmosphere. And it turns out that water is also a greenhouse gas. If you vaporize out into your atmosphere, you can have a greenhouse effect. That raised the temperature even more. CO2 began to outgas out of the rocks. And at that point, it was a total greenhouse runaway. And that's what I mean by a planet that just goes unstable. So why did this happen? Because when there was no water, the crust was rigid. Venus doesn't have any plate tectonics. It trapped its heat inside the planet. The heat couldn't get out, and as a result, Venus has had a series of fantastic volcanic episodes that resurface the whole planet once every billion years or so, completely different from Earth. So here's the summary. Just by being slightly closer to a sun, your evolutionary paths can diverge greatly. And Venus is an example. Okay, last point. Do we need a moon for complex life on Earth? Some people say we do. The moon formed in a potentially rare giant impact. The solar system was full of bodies. A big one crashed into the Earth. This happened soon after the formation of the solar system, early on. And we note that today the Earth has an axis tilt of 23 degrees, and you can tell from paleological information that that tilt has been the same, pretty stable, for billions of years. This is odd, because the pull of Jupiter and the other planets would tend to make our axis wobble. So it is thought that the presence of the moon in orbit around us actually stabilizes our axis. And the seasons might be very well a forcing function, creating more complex species through evolution. And if so, then we need a moon to stabilize the axis tilt. So in the rare Earth equation, some people put a moon in there as being required for advanced life. Okay, so I've touched on just a few of the factors that have been discussed as important for generating complex life on Earth. Let's now compare what we see in our solar system with what's been discovered around other stars. So the very first planets that were discovered around other stars were very massive, so-called hot Jupiters, and they were easy to find using the so-called Doppler wobble method. But since then, hundreds, if not thousands, of more planets have been discovered from this satellite, the Kepler satellite, using transits. So when a star goes in front of its sun like this, it blocks some of the light, and that can be managed and detected. And the nice thing about detecting planets this way is you get a measure of how big they are, how big their radii are. So here is a summary of the current detections of planets using these various techniques. And this plot shows you the mass of the planet in units of the Earth versus the period of the planet in days. And let me just point out that this is a logarithmic plot, so that every tick here is a factor of 10. This would be 10 days, 100 days, 1,000 days. And here's the Earth at 365 days, okay? And this axis is the mass. So this is one Earth mass, this is 10, this is 100, and this is 1,000. Okay, so what you notice on this graph here is that there seem to be three classes of planets as discovered so far. There are these hot Jupiters, which are massive and close to their sun. That's what I just talked about. They were the ones that were first discovered. There seem to be a whole bunch of Jupiter-like planets farther away, and there's a gap in there. Nobody knows why. But the real surprise was this population of planets, which also came from Kepler. They're called close-in super-Earths. So let's review those. They have planets around a few to 100 days, okay? And they have masses between 1 Earth mass and roughly 10 Earth mass. And here's Uranus in our solar system. So they're a little bit smaller than Uranus, but bigger than Earth. And they have earned the name close-in super-Earths. And I personally think that this is a PR swindle because I think the astronomers who are discovering them would like us all to think that there are Earths out there. But in fact, most of these objects are nothing like the Earth because we think that there's a line in this graph, which is the upper limit to have a rocky planet. And if you're more massive than that, then you generate a big envelope the way Neptune and Uranus have. And so those planets would not be very useful or interesting for complex life. So we really should be focusing our attention down on these planets here, the smaller ones. Okay, now, here's Earth, and you will observe that Earth is rather far from this distribution. Does that mean that there aren't any Earths? And the answer is no, because it's much harder to detect objects in this direction. It's harder to detect objects that are farther from their sun, and it's also harder to detect objects that are less massive. So a question is whether or not really this is the right distribution, and we just haven't detected all of the objects in that part of the distribution. Okay. And just to illustrate how hard it's going to be to interpret these distributions, I put Venus on here. Supposing we had detected an Earth and a Venus around another star, we could very well be tempted to say that they have the same histories, and yet we can see in our own solar system that they've had wildly different histories. So the net result is we do not know at this present time whether there are a lot of Earth-like planets out there. We don't know because we haven't probed this region of the diagram, and we don't know because we can't predict very well from this graph what the life history of a planet is going to be. So, do we have a rare Earth or do we have a common Earth? We don't know. And when we're thinking about the implications of our Earth, we better take both possibilities into account. All right, I've been summarizing present situation. Now let me move on to thinking about the future. I promised you some prognostications about the future. The way to think about the future is to think more about the past. The history of Earth shows massive changes. I've been mentioning a few. Earth was once a water world with virtually no land. Did you know that at one point, actually maybe even 2 points, it was completely frozen over from equator to pole? It was called snowball Earth. And it's very hard to get out of that state. For quite a while, scientists thought you might get stuck in that state, but they figured out a way. Nevertheless, absolutely, totally different from our current situation. O2 has been as high as 30%, and amazingly, CO2, which we're worrying a lot about today in climate change, has been as high as 20 times our current level of CO2. How can the Earth recover from a situation like that? Because of plate tectonics. The extra CO2 was subducted back into the crust, given 100 million years or so. That's how long it takes the cycle to run. But that's the stabilizing influence for our planet. The moon was generated out of the Earth by a giant impact. At the beginning, it was very close, only 15,000 miles away. The tides in that young ocean were 1,000 times higher than today, and the day was only 5 hours long. Imagine tides that are 1,000 times bigger. I mean, now they're a few feet. That's a tide that's a mile high. And it's running at intervals of a couple of hours or so, you know? So again, a planet that looks totally different from what we know today. And if you don't like that, that's very far back in time. Even very recently, sea levels have varied recently by hundreds of feet. Our ocean volume is changing drastically. Okay, so now let's think about moving what's going to face us in the future, and I'll consider 5 perils here that are pretty likely to challenge intelligent life on Earth going forward. The first is solar warming. The sun is going out slowly, and in the process it's brightening at a rate of about 7% per billion years. So this is going to lead to steady global warming, independent of people, and this is going to cause a loss of CO2 due to this process that I told you about, rock weathering, which takes CO2 out of the atmosphere and puts it inside. It's going to go faster because chemical reactions go faster at higher temperature. So CO2 from this process is going to disappear. And the first impact, 600 million years from now, we will not be able to have plants doing photosynthesis anymore because there won't be enough CO2 in the atmosphere. So the conclusion from solar warming, the sun is going to last billions of years more, but in just a few hundred million years, we're going to have a loss of habitability here because we're going to lose our plants. Okay? The next phenomenon here is the explosion of nearby supernova. And by the way, I called these disasters, right? A disaster is an ill-starred event. Aster is Latin for star, so this is a bad star. Seems very appropriate, doesn't it? Okay. So a nearby supernova explosion sends out ionizing radiation that will destroy our ozone layer. The danger radius, about 30 light years from now, half of the ozone layer is destroyed. You remember ozone protects us from solar ultraviolet light. And the effect would last for several centuries. The frequency of nearby supernova at that distance is every few hundred million years, and so I've concluded a few hundred million years to loss of habitability here. We had 600 million, now we have a few hundred million. Okay, another disaster is comet asteroid impact. We've all heard of this Chicxulub asteroid impact 66 million years ago in Yucatan, Mexico, which wiped out the dinosaurs. So a 10-kilometer asteroid will destroy all higher life. A 1-kilometer asteroid wipes out agriculture, which is pretty bad, so let's focus on that. The frequency of 1-kilometer impacts is about every million years. And fortunately, asteroids have long warning times. And NASA's already started a Space Guard program, which is finding objects bigger than 1 kilometer. That's our magic size here. And they have a technology that will divert asteroids up to 140 meters in diameter, not 1 kilometer. So I conclude, for our point of view, we have major inconvenience is going to be inevitable. Yes, they're going to come our way. But we better invest in some technology that will work up to 1 kilometer or so, and I think if we worked at it, that would be possible. Next thing is ice ages. We do not understand them. There are multiple factors which go together: the obliquity of the Earth's atmosphere, the ellipticity of Earth's orbit. There's something called the Milankovitch cycle, continental drift, and so on. People try to make models, but they're not yet very successful. We do know from the paleological record that actually the current situation in which we have glaciers is unusual. 80% of the Earth's history was too warm to have any glaciers, and Earth was ice-free throughout that period. So if we were to lose our glaciers, from climate change, doesn't necessarily mean that there's going to be a big impact on Earth climate. So ice ages, they come and go. The last one ended 10,000 years ago. Major inconvenience because they do affect agriculture, but will not affect habitability. My last disaster is volcanoes. This came as a great surprise for me. This is probably the worst one. There are two kinds of volcanoes: the explosive kind, which put out a lot of cloud and ejecta like this one, and this is the danger level, 1,000 cubic kilometers. If you put that into the atmosphere, then you get a global winter, you block out the sun, major disruption. That would be 100 times Krakatoa. But there's another kind of volcanism, which is a slow ooze, and can emit huge areas of lava, last millions of years, and the largest extinction in Earth history, 250 million years ago, was thought to be caused by that kind of volcano. Okay, focusing on the explosive kind, they occur about every million years or so. Modern mammals have survived unaided for about 50 million years, so apparently higher life can get through these episodes. So I conclude major inconvenience inevitable and 100 million years to loss of habitability with a big question mark. Okay, so trying to summarize these 5 disasters, they all sort of add up to a few 100 million years or 100 million years of... What happened here? There we go. A few 100 million years of habitable planet in front of us. So that's what I'd like to assume for the rest of my talk, that our species has a good 100 million years to go on this planet. All right, so let's have some lessons from cosmology. Lesson number 1, we got here according to the laws of physics. We understand this process pretty well. We are subject to these laws and we have to live within them. The subtext there is there aren't any miracles here. Okay. Lesson number 2. Okay. Lesson number 2 is that Earth will provide a livable home for us for at least 100 million years and maybe longer. And therefore, this is one of the prime conclusions of my talk. We've been given a precious gift of cosmic time, and my question is, what will we do with it? Okay. And here's something to think about. We're the first generation of human beings to realize that we have this challenge. Nobody has ever put this knowledge together before to think about these issues. Okay, so what are we going to do with it? Here's what we're not going to do. We're not going to engage in steady growth, which is what we've been doing for the last several hundred years. Why not? You know, our government, our economics people, they love to tell us about economic growth, and the standard growth, which is normal, 3.5%, correct? Okay, I read to you from today's Wall Street Journal. Sclerotic growth is America's overriding economic problem. From 1950 to 2000, the U.S. economy grew at an average rate of 3.5% annually. Since 2000, it has grown at half that rate, 1.76%. I'm a great reader of the Wall Street Journal. I believe like 10% of it, but I think it's very good to read the views of people who have different opinions from you. And what strikes me is the conflation of growth, specifically economic growth, with steady state. And if you are not growing at 3.5%, which has become the normal target, then you are actually declining. And the language reflects this constantly if you start paying attention to it. All right, now why are we not going to grow at 3.5% for 100 million years? Well, what does this mean? That means that every year our GNP gets bigger by that factor, so put 100 million of those together. This rate of growth has conveniently, it's easy to remember, a doubling time of 20 years. So in 40 years, GNP's gone up by 4, and in 80 years, rounding, that's a person's lifetime, that's my lifetime, getting there, a factor of 16. Wow, and I didn't even notice that. Okay, so this is the miracle of compound interest on cosmic time. You know, what happens if we run this for 100 million years? Who can just do the math in their head? Here's the answer. Okay. All right, so that's a big number. And we don't even have to hang around for 100 million years. I think, I'll just bet, we could talk about this in the discussion, that you all have an instinct that we are reaching the end of our period of fantastic growth on this planet. 40% of all water falling on the surface of the earth is now used. 90% of all arable land is being farmed. We're just running out of room, you know. And so this complaint that we're not growing at the rate that we used to grow, maybe it reflects the fact that we're approaching Earth's limits. Now, I know, I mean, who said that? Malthus, right? And he is derided. Well, the Wall Street Journal thinks Malthus is really, you know, so wrong, so wrong-headed. They take out after him once a week or so. There's some statement about how wrong-headed Malthus was in telling us that the population couldn't increase. Now, the problem is not so much the population, it's the economic growth, it's the use of resources, it's the stuff that we're producing is causing the demand on the planet to increase. So I know that Malthus is derided because he was just ahead of his time, and maybe I'm ahead of my time, right? You have to hit these things correct, but I'm sort of betting within the next 100 years the Malthus scenario is going to come true. Well, what would be sustainable growth on cosmic time? Let's give us another factor of 2 over 100 million years, and this is what it is per year. So it's quite obvious that there's really, if you're planning to be an intelligent civilization and take advantage of this period of time, then there's no net increase in the resource use. And furthermore, even probably more important, the waste has to be reduced to levels that can be completely recycled. You know, plate tectonics will recycle if you wait 100 million years. It takes all that garbage and puts it into the core. Okay, so what is my vision for the future? I'd be interested in hearing yours. I call it the 1% solution. Okay? This is a sustainable society assuming, and this is a big point, our current human genome. That is to say, a genome of an intelligent species that likes the things we like. What do we like? I actually gave some thought about this. What is the most important thing that we seem to like? I think, in addition to reproducing, eating and reproducing, I think stimulation and novelty are the most important things for people to live a valuable life. And so that means that the number of people on the planet should be maximized. I'll save the planet if I get down to 50 people, but I don't think they would have very interesting lives if we did that. So my goal is to reduce the environmental impact, and I have to choose some level, some percentage of the current impact, and arbitrarily, completely out of nowhere, I say 1%. Just out of a conviction that 10% is still not small enough compared to the current environmental load that we're putting on the planet. So to be safe, I'm getting down to 1%. And what does that mean? In order to evaluate their quality of life, we have to figure out how much energy they're consuming per person. Because this thing turns out to set your standard of living. How many ergs are at your disposal really determines your quality of life. So let's assume a factor of 2 gain over whatever they're doing in Europe these days, give us a little bit of growth in that figure. What's the answer? 50 million people in this world, just about the state of California. When did we have 50 million people? Start of the Iron Age. That was 1000 BC. And how do we gauge the productivity of this world? Well, it's obvious. How many astronomers does it have? No, seriously. This is as good a way of doing this calculation as any, right? There are, if any, there are only 100 astronomers in this world. There are only 100 astronomers in California. So it's not a bad calculation. Right? This is profound. I mean, those astronomers are not launching space telescope. I'm making the point, we have hard choices coming up. It's not as though it's bad to have lots of people. The amazing things that we have accomplished because we've had lots of people, billions of people. But going forward, I don't think we can afford those people. And so what kind of life are we going to craft for ourselves? It's going to look very, very different from the life that we've had recently. Okay, I'm almost finished. Here is a cartoon which was popular a while ago, okay? Remember this film by Al Gore? I think actually this film has completely missed the point. It has missed the cosmic point. Here's the cosmic version of this. Okay? This is the fairy tale, and this is cosmic reality, which is really very different from any picture that sustainable agriculture or sustainable living is painting for the world as we know it. My picture is much more severe. Okay, let me close by posing some questions that I think come up as a result of these thoughts, a suite of new and thorny moral issues. Why do I use the word moral? I use the word moral because that's a shorthand for me for describing the logic that I go through in order to make a decision, a meaty decision, a weighty decision. And I could pray to God, I could read the Bible, I could read philosophy, I could look into my soul, whatever that means, in order to make these decisions. Those are moral decisions for me. And here are some questions that have come up. What are our obligations to future human generations? Where do you read in the Bible any statement in Western religions that we should be taking care of generations that are 10 million years in the future? It's not even mentioned. People don't even think about it. You're lucky if you think about your grandchildren and your great-grandchildren. The obligation to the trajectory of the human race is never even considered. Likewise, other species are given pretty short shrift, and protecting the planet has everything to do with their welfare. Do we have a custodial responsibility for our Earth? And does it differ if Earth is common in the universe or if Earth is rare? Take a beetle. Is this beetle worth more because it's in Yosemite or downtown San Jose? You know? Okay. Yosemite is rare. It's a very beautiful place, everything associated with it. That's an ecosystem. Should we be working hard to save that ecosystem and we let San Jose go down the tubes? I don't know. Okay. All right. This makes me think of the notion of galactic national parks, in which there might be planets of uncommon worth. Venus would not merit a galactic national park. Maybe Earth does merit a galactic national park. Maybe we'll find that Earth is so wonderful and special that we would want to preserve it. I think deep within our genome is the desire and urge to preserve rare things. Remember when they blew up the statues, and the Taliban blew them up? That we felt a loss. Supposing the state of California, which it might do, signs a contract to some hotel developer to develop in Yosemite, and Yosemite is destroyed. We reject and we want to avoid actions like that. We feel that they're just not harmonious with our values. And so, you know, how does this notion, how does this impulse play into our desire to protect the Earth? Is there any intrinsic value in the future activities of humankind, of and by themselves? And has there been any value thus far? And to whom? Right. If the universe is pointless, that's the statement that made by the famous physicist Steven Weinberg, how do we find meaning in it? And now we have the whole story of the universe, and it can show us where we're going. It's hard for me, personally, to find meaning in the universe. And so how am I going to find meaning in my life and our species' life? And finally, where does our moral code come from? I happen to think that it's genetics-based. It's grown up along with the rest of our genome as a strategy for a social animal. But some people believe that it's religious. Doesn't matter here. Will our moral codes adjust to deal with these completely new questions, which are pretty much left out of the discussion up to now? So maybe we can discuss these things. So my last picture is a picture of Earth. Okay, you're saying no, no. This is a picture of Saturn. It's a very unusual picture of Saturn. It was taken by the Cassini spacecraft that flew around behind Saturn and looked back towards the sun. So you're seeing the rings of Saturn illuminated by sunlight. But actually, it is a picture of Earth. Okay. See that right there? Okay. That's Earth. I like this picture. It really puts us in perspective. It's the picture of Earth that was taken from thus far to date the largest distance. And returning to my theme before, this could depress you. Yeah, it could make you think that in fact we're very insignificant. But I think I've tried to make the point that in fact there are some very special things about us, and that we have a great opportunity. We have an opportunity of 100 million years. We have a wonderful planet, a fertile garden that is ripe to create complexity, and we have 100 million years to farm it. A jewel of the universe, really. What will we make out of this? And I think that's the question before us right now. I welcome your thoughts. Thank you.
Have you run this past Jerry Brown?
One other picture, we repeat questions for well audience as well.
Okay.
All right, so question in the back.
First of all, I congratulate you on the creativity of your entire speech. But you seem to be assuming that human beings are going to stay like they are now for the next 100 million years. Where do you consider, if you think it's relevant, the effect of artificial intelligence and the so-called singularity and the voluntary convergence that some people see between what they refer to as the made and the born, incorporating technology and creating different types of human beings 100 million years from now, very different from what we are now.
All right, so just make sure the web audience heard that. The question is basically about, in 100 million years we could evolve amazingly, especially artificial intelligence and several other things that he mentioned. How do you respond?
In a couple of ways. Great question. That may be our salvation. That is to say, to save us, we need to change us. One thing that immediately comes to mind, though, this artificial intelligence, my first thought when you mention that word is computers or something like that. So I went off and I did a little bit of research on the energy efficiency of computers. Remember Watson? Right. So Watson can engage in so many flops per second, and you can compare that to the human brain. And the brain uses so many watts of energy. And what does Watson use? Watson uses 10 to the 5th times as much energy per flop as we do. So I don't see much prospect for actually building machines that could compete with biological intelligence. Now, on the other hand, maybe we could alter bodies and brains, and I think that's very interesting. I'd like to contemplate that. However, if you think about the last part of my talk, really the essence was we're not going to grow anymore. And I think that moral, that lesson will be true for whatever kind of life form we're having. The only real change to the logic, I think, is the notion that we will escape to other planets. And we will continue to be addicted to growth, and we will manage to support that growth by expanding our footprint in the universe. That might be possible.
I don't have a question, but I want to point out that somewhere within the last 2 weeks, I saw a program on PBS where there was a panel discussion of about 5 people, and they were not astrophysicists, but a real estate developer, someone concerned about pollution control, someone concerned about designing cities and talking about the number of people in the city or how big a city can be. There was a guy there from the EPA, the Environmental Protection Agency. he claimed that there was no problem because so long as you let him do his job, we'd have no problems. But with the rest of them, what I'm going to say to you is with the rest of them, they were coming to the same conclusions that you are. They actually spoke of limiting the size of cities, limiting the growth. One gentleman was proposing solutions to all our problems, and he actually was saying that we don't want to continue with a growth rate of 3.5%. They were speaking your game, and they weren't astrophysicists. They were ordinary people.
I guess we should repeat that, right? I tried to do it very briefly. The gentleman in the audience pointed out that there was a discussion on the radio.
Yeah, on TV.
On TV.
PBS.
Right, by non-astronomers, a varied cross-section from different walks of life of people who are suspecting that the limits of growth are finally arriving. Yeah.
You had mentioned that the goal for environmental impact was ideally 1%?
Totally arbitrary, yes.
Okay. And earlier on your slides, you mentioned that sustainable growth should be 0.00007. What's the difference?
Oh, the 1% was to reduce. That's not a growth factor. Okay? I need to repeat the question. This woman is comparing two numbers in my presentation, 1% in one location and 0.00007 in another location. The 1% is not a growth, and it was meant to say at the moment we're putting some load on, some demand on the environment. I thought that to be truly sustainable in future, that should not be any bigger than 1% of its current value. That's the big factor that causes the reduction in population and so on. The other was a growth factor, 0.00007, and of course what I really meant was it was 0. Yeah.
Do we see plate tectonics on other planets in the solar system? I think we've seen evidence even on Pluto of plate tectonics.
Good question. Do we see plate tectonics on other planets? And the gentleman specifically mentioned Pluto as a possibility. So no, we don't see plate tectonics like ours. There's no tectonics on Mercury, Venus, or Mars. And we can't see into the cores of Jupiter and Saturn and so on. But Pluto, I think, is a slightly different situation. It is a basin that is full of nitrogen molecules, N2. And there's some internal heat in the planet, probably due to radioactivity. Nitrogen, frozen nitrogen 2 is solid. Nevertheless, this substance is actually slowly convecting. But what we don't have, that's like a basin, that's like a pot of water that's convecting. It's not moving plates around on Pluto, which is the key point. Yeah.
So one of the justifications for projecting growth indefinitely is things in line with the American exceptionalism, or that we can, we've always figured out a way, and it's through this sort of narrow prism of this history that we've seen, and we've always figured it out, and we'll continue to figure it out. And that can be scaled up to the human race and the idea of the singularity. Oh, well, we'll just get the machine, think out of it. So setting that aside, is there a parallel that can be observed between that sort of thinking and the, I'll coin Terran exceptionalism that says that our planet has to be special because we see how special our planet is, and we haven't figured out how that many planets can have these conditions. And obviously there's a lot of really good thinking underpinning what the building blocks of life, but there's only so much imagination to go around. So
that was a complicated question. I'm not sure. Okay, it has something.
I got the question.
I try to shorten it. Maybe is there some relationship between American exceptionalism and maybe a species exceptionalism that says we are a species, are special and deserving, and maybe that extends to the fact that because we are special and deserving and exceptional, we got this planet and we deserve this planet. And I don't know if I'm kidding you or
the one part I probably didn't get across was the scientific idea of the two things you set aside. That I'm thinking that I'm eschewing the American exceptionalism thing and even the expansion of that, but the idea, the focus that Earth must be special as opposed to mediocre might be just as narrow of a perspective. Is that also potentially as narrow a perspective as this idea that humans can think ourselves out of it?
Okay, is Earth being mediocre versus rare, are these... I'll try. So I just think those two extremes are selected for purposes of discussion. You know, they represent opposite ends of a spectrum of probability, and so people find them useful to write books about, which they do.
In the back there. Yeah, no, you?
Oh, great.
Right there.
So as a molecular biologist, you know, we study populations all the time, and when you hit a certain growth phase and you exhaust your resources, that population comes crashing down. And I teach on the public health campus here at Hopkins, and the inevitability of a major pandemic occurring in the next several hundred years, let alone 100 million years, looms quite certainly. So, you know, I think there are factors in this trajectory that are fairly inevitable in terms of population growth imploding based on our inability to manage the impending epidemics that we have very little to defend against.
Okay, so I do have a response to that. I don't know how good it is. The question is, won't we have pandemics? You didn't talk about pandemics, and they're going to act to reduce the size of the population anyway. So I didn't talk about that because statistics on previous pandemics, they're not efficient enough. They don't kill enough people. Seriously. They're sort of, you know, you look at the population of the world, which has been steadily going up, and there's this, you know, the Black Death, 20%.
We keep growing, just the same.
Yeah, so they're temporary, but I don't think we should look to pandemics to solve our problem. That's good, an asteroid impact, yes.
Pandemics, yeah. Okay, the senator there, the white shirt.
Yeah, your model, 3.5% growth, from a financial standpoint, you just blew up the entire capitalistic model.
Thank you. Yes. Okay, so that,
some of us realize that.
Yeah.
But yes, 3.5% is not a sustainable rate of growth.
Well, I'm so glad you brought this up. The question is, if you abandon this rate of 3.5%, maybe you now insist on 0 just to be consistent here, what happens to modern economics as we know it? So I think this is a huge issue. I really think that interest, investment, stock market gain, I suspect, I'm not an economist, but one of the very first things I really want to do is to meet some economists who are even willing to think about this, because nobody talks about this. Could you have a pension? Could you make an investment during your lifetime and then reap the rewards of that if there's no economic growth? I'm extremely dubious.
Adam Smith predicted it.
Ah, okay, I need to look at that.
Most people haven't read the second half of the book.
Go ahead.
Yeah.
Yeah.
Oh, okay. I can't help but think, my first thought is, gosh, the children.
Mm.
Oh, I know. Gosh, is that's, wow. Yeah, the children, and hey, I love science, but gosh, just I heard the economy and this, and you know, besides the fact of, you know, 50 years, 100 years, 1,000 years, 1,000,000 years, you know, just that we're and if love doesn't come to, also the probability of trying to get to another planet, absolutely. And you know why? And you know who it's going to be? It's going to be Donald Trump. I'm only kidding. My point is, it's going to be the elite. Hence, if you look at history and time of humanity. So, love better come to be. That's the miracle, by the way. And how did you know something was sticky? There were so many questions that I wanted to ask, right? You said something was sticky, and you had photos of it, but how do you know it's sticky?
They do experiments. The question is, how do we know that interstellar grains are sticky? We can do experiments.
You're on talk within 15 minutes. I know, I was trying to write stuff or whatever. And, all right, just wanted to say, I've been to many talks here. That was one of the best talks that just was.
Thank you.
And did you do your presentation on the shots? Put it together, how it flowed?
Sure.
Oh, God, I loved it. Yeah, it was just very, yes, it was great. Thank you. Sorry, children.
The orange there.
So the financial markets have adjusted for the inability to grow at 3.5% called derivatives. And no, I'm not joking. I mean,
I know you're not.
so the market was created so that they create additional markets laying on top of other markets on top of other markets, and they're trading nothing.
Yeah.
So they have accommodated for that, and so a lot of, and I work in financial industry, so yeah, so I see how it plays out, and so really nobody's getting wealthier in the sense. It's just the money's being shuffled differently. So, but anyway, to make it relevant to the conversation, more topical, this whole thing prefaces on us wanting to survive, and there's a substantial reasoning behind us wanting to survive, and the scope of this is way beyond what any of us can truly comprehend. And there are cultures on Earth, like the Chinese, who don't think that far ahead, and in fact don't even believe in savings. So to convince a third of the world's population into
Chinese stayed at 30%. They wish they would save less so that they would be a consumer society.
Save, yeah, but they don't save for the future beyond them. So they consume resources at a rate in which they're aware of the level of impact in the future, but they don't accommodate for those future generations in a way in which it's sustainable. So we already are at a point now where the population on Earth isn't existing to sustain itself. So whether or not we want to think that some asteroid's going to hit the Earth, we're by far our worst enemy. And we're the ones that are going to find a way to call our herd. And we're not going to wait on a pandemic. We're going to end up doing it to ourselves.
We're going to have to what?
We're going to do it to ourselves.
All right, and we're getting over time here. I saw this gentleman in the black, green, and then we had the woman back there, okay? And I'm going to have to cut off questions there, I'm sorry.
Yeah, the protogalactic dust, did you mention what its principal chemical composition was?
The question is, what's the composition of the galactic interstellar medium dust? There seem to be two basic families. One is carbon, graphite, and then the other is a mixture of iron, silicon, magnesium. Think of rocks.
What was the genesis of that?
It grows in the atmospheres of stars, also in supernova explosions. Material goes out in an explosion or an expansion, it cools, and if there's heavy elements like that in the star, then the heavy elements condense in tiny grains, much smaller ones, and then that material seeds goes out into the interstellar medium where it accretes more similar atoms from the it's really like cigarette smoke. If you wanted an analogy, the carbon part of it is very much like cigarette smoke, about the same size particles as cigarette smoke.
Sticky.
And it is sticky when it gets.
I think there's hope because the fact that when I watched your presentation, almost none of this was known when I left high school. And so I think the rate of information is growing at much faster than the rate of financial growth or anything like this. And I think the hope is we'll get smart enough to use the information we have to make some intelligent decisions sometime, maybe not this year.
So the comment is it's a race against time. Is the information coming too fast for us to even use it? Will we wise up soon enough?
If you go back to the number of people in the Iron Age, you'll have fewer people to process the information.
All right, last question.
When conditions for life were discussed, were non-planetary like life taken into consideration? Like, for example, on moons of...
Right. So some people have said that life can actually start in interstellar space. I don't know too much about that. It seems unpromising because it's low density. Moons, definitely. In fact, there's a candidate in our solar system, Europa. One of the new things, you know, the old picture was that life would begin in warm tide pools with some stimulating UV light from the sun. But actually, a more compelling picture these days is that it began under the sea in these so-called hydrothermal vents, which provide entropy and energy gradients that are conducive to the chemical reactions that you need. So Europa is close to Jupiter, and it's being squeezed all the time by Jupiter's tide. And the surface of Europa is icy, but it's thought that there's a melted ocean underneath and probably has hydrothermal vents in it. Probably the core of the planet is hot. So people wonder whether or not Europa might actually be a source of life. One of the things that's clearly emerging, though, is, are we interested in microbes? Microbes might be very easy to make. But moving from microbes to so-called eukaryotic cells, those are the cells that have nuclei and organelles and mitochondria inside them, that's what it takes to make a bigger animal. And that's what it takes to be interesting. And so microbes may be common, but eukaryotes might be very rare.
Okay, I'm going to have to cut you off there. All right, join us next month for the Nicole Lewis. We'll be talking about exoplanets. And someone gave me a flyer for a planet walk happening this Saturday on the Baltimore-Annapolis Trail. You can walk the solar system. If you want more information, come on down and take a look at this flyer. We'll see you all in June. Thank you very much.
Bottom of the 8th inning, Baltimore 4, New York.
Oh, okay.
That was an absolutely terrific speech.
Thank you.